Turn now to some less biological self-assembly procedures. And the first one I want to talk about is the formation of molecular monolayers on surfaces. There's a vast literature of this field, and I'm just going to focus on one procedure, which is a very well-known one, which is the attachment of molecules to gold, and in particular alkane chains, which, as you remember, we discussed before, each one of these vertices is a methylene CH2, and the group at the end is a CH3, but then attached at this end is a sulfur, terminated in a hydrogen before it interacts with a gold surface. The sulfur-gold bond is actually very strong. So if I have here a gold surface, the interaction free energy between the sulfur and the gold, so the proton is lost as the sulfur coordinates the gold, is about 184 kilojoules per mole, which is about 300 times kT. Now, in fact, it turns out that molecules are rather mobile when they interact with a gold surface, and we'll talk about just why that is in a minute. The way this procedure works then is to take a solution of thiol-terminated alkane chains, and this is a fairly length-dependent technique. If the chains are below about 6 carbons in length, well-ordered films don't form. If they're too long, 18-20 carbons in length, it's difficult to dissolve them. So there is a range then from about 6 to 18 carbons for which this technique will work. This is put in contact with the gold, and the first step is that the molecules come down onto the gold, lose that hydrogen, and associate with the gold in some disordered form. However, over time, the molecules move on the surface, and we'll discuss just how this might be. And as more of them absorb to the surface, they push their neighbors away through van der Waals interactions until eventually the result is a well-organized, densely packed monolayer, usually tilted to allow the closest packing of the alkane chains. And by tilted, what I mean is this angle between the normal and the molecular axis is some small amount. So this process, very simple: dissolve the alkane thiols in a solvent, leave them in contact with the metal surface for a number of hours, can produce beautifully organized monolayers, as you see in this scanning tunneling microscope image here. You can see the heads of all of the molecules quite clearly, and you can see domains between individual molecules. Notice, however, these holes in the film, and we'll talk about these in a second. So how come these molecules are mobile? Well, it's still something of a topic of debate, but the most likely picture is that on the gold 111 surface, when a sulfur adds to the surface, it does indeed form a strong bond to the gold atom that it bonds to, but this weakens the interaction with neighboring golds. So the mobile unit is actually an SAU, and most likely what it does is to move around on the surface until it forms a structure somewhat like this, which is then densely packed. So this mobility of the gold attached to the sulfur has some important consequences. One of them is that if the gold surface starts out flat like this, then as the sulfur binds and pulls atoms out into sites like this, these atoms, of course, remove atoms from the surface, and they result in the formation of pits that are one gold atomic step deep. And that is what you see on this scanning tunneling microscope image here. If you zoom in on the pits, you'll see that they're also covered with a monolayer of the alkane thiol, but the step down here is precisely the height of a single gold atomic layer. A second consequence of this weak bonding between the gold bonded to the sulfur and then the bonds to the neighboring golds is that the bond itself fluctuates a lot even at room temperature, and that's what's shown in this panel here. What you see is a molecule that's been inserted into the film that is higher than the alkane thiols around it, so it shows up as a bright spot. In this next scan here, it's gone, apparently disappeared. Only it didn't disappear because it comes back in the same place, so it's not leaving the film. It's just that the electrical contact to the surface is fluctuating, and this gives rise to the scanning tunneling microscope image switching on and off. Let's turn now to self-assembly of structures by kinetic control of growth. This was actually first demonstrated in 1857 by Michael Faraday, who reduced a gold chloride solution probably with sodium citrate, but I'll just write a reducing agent here, to form a gold solid precipitate, and then presumably HCl and Cl2. I didn't balance this equation. He did it in a mixture of carbon disulfide and water. Now, the gold nanoparticles will enter the CS2 phase, but once they enter the CS2 phase, so I'm showing little droplets of CS2 here, once they enter the CS2 phase, they no longer have access to gold ions to continue forming the precipitate, and so they remain as nanoparticles in the second liquid phase. The picture here is of a quantum dot of cadmium telluride, or cadmium selenide, and this is made by a different method in which a syringe containing one of the ions in the final solid, let's say cadmium, and it's of a cold solution, is injected into a hot solution of, let's say, selenium ions. The two react to form an insoluble salt, but because the solution is cooled by the injection of liquid, the growth of the nanoparticles terminates early. They don't form large aggregates, but rather a suspension of small nanoparticles. A second step, interestingly enough, is then to cycle the temperature of this suspension from a low temperature to a high temperature and back again. It turns out that because of the importance of surface effects, so that the free energy per particle, if you remember, was like n to the 2/3 over n, the smaller particles have more driving free energy for incorporating extra atoms, and so thermal cycling, the small particles grow at the expense of the larger particles, and this tends to produce a more monodispersed population of nanoparticles. This process is called Ostwald ripening. Shown on this slide is another approach to making, in this case, nanowires, which is the use of chemical vapor deposition. So, for example, the decay of silane to give silicon. Now, if this is done in the presence of gold nanoparticles that have been placed onto a surface, the silicon is soluble in the gold, and so the gold will begin to dissolve silicon, eventually saturating with it, until the silicon starts to precipitate out of the gold and grows out of the gold as a nanowire. Nanowires microns long and just a few nanometers in diameter can be grown this way. It's also possible to grow nanowires from solution by playing tricks to encourage growth along one crystal axis.